is, so all this eigen stuff, we had A, and from A we were able to find the lambda I and the xi eigenvalue vector pairings, right? So we find an eigenvalue, we find its associated eigenvector. We know that no matter what, this is always true. A times x is x times d, where x is just simply collecting all the x1, x2 up to xn, and then the d is just simply the eigenvalues lambda 1 down to lambda n in a diagonal element, right? No matter what, this is true, right? But on the other hand, if the inverse exists, we could take two variants of this. We could say x is equal to xd x inverse, or if we wanted to, we could say that x inverse a x is equal to d. The first one is called a factorization. The second one is called a diagonalization, because A is being turned into a multiplication of matrices. That's a factoring. All right, A being multiplied stuff becomes a diagonal. That's a diagonalization, right? So that's a factorization. This is a diagonalization. What's necessary for the inverse of this bunch of eigenvectors to exist? They need to be independent, right? X of I must be linearly independent. How do you check for linear independence? Let's say you didn't want to check for independence and you just looked at the eigenvalues. Can the eigenvalues help you? If they're all unique, don't even worry about checking. If they're unique, their vectors will be independent. On the other hand, what if there's a repeated eigenvalue? What are you going to have to do? Check. And how do you check to see if a bunch of vectors are actually independent? We'd look for free variables, but is there a thing that checks for independence and it determines such a thing? The determinant, right? Right. Just take a quick determinant. If it's what? If it's 0, what does that mean? They're dependent. If it's not 0, they're independent, right? So we continue to use all of this knowledge to check all of this out. And so if this works, this thing happens. Now, along with that is some other things that we can pull back. We could actually say things like, we also know from the past, if A is n by n, we can think of it as a transformation, right? Or a function that does what? Over here is Rn, over here is Rn, and then A moves vectors, right? It's a transform. It transforms space. We've already talked about things like that. Okay. What's the standard basis of Rn? Rn, standard basis, is what? 1, 0, 0, 0, and then 0, 1, 0. How do we normally write that? E1, E2, up to En. If I wrote it as a matrix, it's the identity matrix, right? That's the standard basis. All right, for Rn, what's its dimension? N. So if I have a basis, how many vectors do I need? N, and they must be linearly independent. So this also tells us this, right? The dimension of Rn is n. So any n linearly independent vectors act as a basis. So we know that, right? We did things before. It's like, and so we would do things like, well, I have n linearly independent, but I want ones that are all orthogonal, so we have the Gram-Schmidt process to generate such stuff, right? But really just simply says if you have n and they're linearly independent, that means it makes a basis.
On the test, are you going to give us the formulas for the Gram-Schmidt?
No.
Okay. For something else? Right.
Yep. So let's go back to A is factorized by AX D X inverse. X is equal to x1 up to xn. How many eigenvectors are there? N. Since the inverse exists, they're actually what? Linearly independent. So if I have n linearly independent eigenvectors, put those two together. What do these act as? A basis. These act as a basis of Rn space. So X is also a basis of Rn. What are some other stuff that we know? We also know change of basis. What if B is, so B equal to, basis 1, basis 2, up to basis n is a basis. What happens when I take B and I multiply it by a vector whose coordinates are in B? What does it spit out?
Standard.
The coordinates in standard. What if I would take the coordinates in standard and multiply them by B inverse? It would take and spit out coordinates in B. That's the change of basis stuff. You multiply by a basis matrix, it'll take the basis coordinates and spit out standard. If you multiply by the inverse, it takes standard and spits out basis B. Okay. So here's the kind of interesting thought. So L is a, now, L is a transform on Rn. And we found A is the matrix representation of L in standard basis, right? So what's going on here? Transforms say that if I take L of a vector x that's in standard form, it spits out some new vector y still in standard, right? So what is matrix A? That says A times a vector that's in standard form spits out a transformed matrix in standard form. Remember how we did that? How did we find A? What did you do? Anybody remember? What do we transform? We transform the standard bases. Where does 1, 0, 0 go? Where does 0, 1, 0 go? Where does 0, 0, 1 go? Where those go, that's your matrix. Is that ringing any bells? See some nods and some blank looks. All right. So I have a matrix that represents a transform. Transforms multiply things whose coordinates are in standard and spits out, it's rotated, right? But its coordinates are still in standard. A is equal to x D, x inverse. That means A times the coordinates of an object in standard is going to be x d, x inverse times the coordinates in standard. That's what this transform is doing. Look at the right-hand side for a second. What's x inverse? It's the inverse of a basis matrix. What would that do to the coordinates of an object in standard basis? This becomes coordinates in the basis of x, which is the eigenvectors. Once I multiply it by it, it tells me, hey, here's your coordinates in standard. Let's multiply it by x inverse. Well, now this is your coordinates according to the eigenvectors. But now, what does D do? Here's a very interesting feature. What is D? D is just simply lambda 1, lambda n, 0, 0. What does it do? All it's going to do is take the first coordinate and multiply it by what? Lambda 1. It's going to take the second coordinate and multiply it by eigen 2. The third coordinate by eigen 3. That's all it's going to do. It's going to take every one of those coordinates and just simply multiply directly what their position is. Hey, coordinate 1, you get a lambda 1. Coordinate 2, you get a lambda 2. But then when I multiply by x, where do we go back to? Standard. Back into standard form. Now, this looks familiar. These are similar matrices, right? So that tells me that when I look at this, A is L's representation in standard. D is the exact same transform, but its representation is in the eigenvector basis. Does it make sense a little bit?
When you say D, do you mean D after it's been multiplied by those?
No, D itself, all alone, is the action of this transform.
These are always going to be the same, correct? It's just going to be the...
It does the exact same thing. It does exactly the same thing. Remember, these are similar, so they have the same actions. So what is it saying? Well, when I look at D, in eigenspace, all it does is just simply stretch along the directions of the eigenvectors. That's exactly what I expected it to do. So what are these transforms? A transform is just going to be represented by stretchings in the eigenvectors. And we could look at this and simply say, when you do a transformation in standard, if you would do a eigenfactorization like this, it's the same thing as saying switch to eigenspace. Stretch according to the eigenvalues, switch back to standard space, and now you know where you are. And so we can sit there and analyze everything is essentially that the eigenvectors are the best vector basis because they're the stretchies. Right? What does it do? Coordinate 2 and coordinate 3 will never interact. I just stretch coordinate 3 and I stretch coordinate 2. That's all I do is just stretch this silly thing. They all just get multiplied individually by lambdas. This only works if what? This thing exists, which means linearly independent, which means it's actually a basis. So all of this simply says it's another way of visualizing. We just simply said, hey, look, turn A into X, D, X inverse. Well, why would I want to do that? Because it actually is a way of thinking about what these matrices do to space or do to your system. All right. So you kind of sort of have that in your head, that this D is just stretching the coordinates of the eigens. Once it's in the coordinates of the eigenspace, it just stretches those coordinates, and then we can switch it back to the standard and ask, well, I like standard because that helps me see where it is in 3 space, right? Because that's usually you have to tell me where it's at. I don't usually think in terms of these eigens, but the eigens help me understand the action of what's going on. Okay.
So basically with the eigenvalues, it's just same, as you said, linear transform, same thing.
Mm-hmm.
This is just the more detailed version of it, basically?
Yeah, it helps us describe in a better way what this thing's doing.
Yeah, okay.
And so let's take an example of this, and we're going to talk about a stochastic process.
So A's transform isn't limited to stretching only, but D's is, right?
Hmm?
It's like A can transform in other
A's doing, like, you would sit there and you do it, it's like, wow, what's all happening? You watch all these events and actions happen, and you can't really see it. But if you go ahead and say, let's take our coordinates and talk about everything in terms of eigenvectors, you notice that in this, where you're taking these special vectors, which might be pointing in weird ways, what this transform does is stretch only in these directions.
And then you put it back in there.
And then we go ahead and put it back into A. So we know how, essentially, so you know how to plot it. Sometimes you don't go back if it's a particular application. And so the application we'll talk about is a stochastic process. All right. A stochastic process it's any sequence for which the next outcome depends on chance. It's like, well, what happens next? Some random event determines what happens next. Things like this, people move, right? If I would simply say, let's look at everybody in the country and I let them move. And you would sit there and say, is there a true deterministic function that makes people move? They lost their job, they need to go somewhere else. They just want to leave to get away from home. They want to go back home, right? There is some deterministic thing, but it's so complicated, what do we simply say? It's random, right? It's just random chance. Why are they moving? Random chance. And if I look at it, I could then start to do probabilities. 25% leave, right? And so many, let's say, and 75% stay. So we did that one whole process of people, like moving away and coming back, or switching leases. Okay, you have to have a vehicle. You're going to go from a truck to a car or to a minivan. So many minivan people keep their minivan. So many minivan people switch to trucks. So many minivan people switch to cars, right? And so we'd have a 3x3 matrix talking about those probabilities. And so that idea of what happens next, I can't tell you who switches. It's random. And so that's what a stochastic process is. It's just simply the next outcome is some sort of random event as we go through it. It depends on chance. Now, Markov process is a stochastic process such that, one, the states are finite. It's like, what are you switching between? A finite number of things. So we just have a finite matrix, not infinite. 2. Next is a function of previous. In other words, it just doesn't simply become next. The previous feeds into the system and it tells you what becomes next. And the third is the probabilities are constant over iterations. You find next, there's a probability of your chances occurring. You have like 50% chance, say it's 75% say, 75% stay, 25% go. It's that way year after year after year after year. That never changes. And so that's a Markov process. Okay, let's look at a particular Markov process that we've already done since, good night, the very first beginning of this class. And so a Markov chain. A Markov chain is made up of one. We have this whole V0 becomes V1, becomes V2, becomes VK, and moves on. These are all state vectors. These are the next, right? The states moving from next to next to next. So we have state vectors, too.
This is kind of similar like recursion.
Yeah, this is exactly recursion.
Oh,
that's all recursion is, just step, 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 step. It feeds back into itself and then goes on. We use a matrix A, which is going to be called our transition matrix. And we're taking A times some sort of older vector becomes the next vector. So A does the state movings. 3, how does this become a stochastic and a Markov process? Is we are going to say that any vector is a probability vector if values are non-negative and sum to 1. So, example, V could be equal to, I got a 1% chance, I got a 90% chance, and I got a 9% chance. And so I could call that, not only could I call it a state vector, it's a probability state vector that talks about, and so this could be things like 1% of people own minivans, 90% of people own pickups, and 9% of people own cars, because we live in Texas. I don't know. I can say that because my friend lives in Texas. And I miss my pickup. Had a great pickup, and then you have enough kids, you can't fit them in the back. You have to get a van. All right. And then on the other hand, if A, which is made up of a bunch of columns, AI, if the columns are probability vectors as well, then A is called a stochastic matrix. These are just some names for this whole entire thing. Okay, we've already done this problem without naming it correctly. If we go way back to page 145, we had population migration. And we were told that for matrix A, it spit out that 94% of the people stay in one particular region, therefore 6% of the people leave. On the other region, 98% stay in that region, whereas 2% switch to the other region. In other words, if I could say this is region A and this is region B, this is region A and this is region B, that's AA, which means 94% stay at AA. That's BB. 98% stay at BB, and so this is the switching B to A, this is the switching from A to B, and so I could just write this as and what is this? This thing, migration. This is a stochastic matrix. And what was the whole purpose of this thing? The whole purpose of this thing was to say, hey, look, how many people do we have now, and how many people do we get to, where what does x0 represent? X0 could say things like, for example, if I said 0.5, 0.5, if that was x0, I don't know what they actually had. But if they said 0.5, 0.5, what do they mean? 50% of the people live in region A, and 50% of the people live in region B. And then the question is, multiply by this matrix, and it tells you what happens next year. Multiply that by the matrix, what happens next year? But I could sit there and say, well, wait a second. This thing, right, multiplying by A, multiplying by A, multiplying by A, could be rethought of as, let's look at this as an eigenvalue problem. So let's go ahead and find the eigenvalues on this, which is nice because you just pull up something. You can do it by hand, like they did in the book, or if you're super, super lazy, and you say octave, no GUI? I think it's no GUI. Yay. And then I could say, okay, A was equal to 0.94, and then 0.02, and then 0.06, and 0.98. Click like that. Okay, and so that's just A. And then they have a nice little function, and I can spit it into two objects. I'll call it little a, little b, and I'm just going to eig of A. So it's going to take the eigens. And what it does is it actually forms the, actually, I probably shouldn't have called it that. I probably should have called it xd, because it finds x and d, right? So what do I know? One of the, if I look at this, now if I look at that, that's kind of weird looking, but that tells me that 0.92, which is one of the eigenvalues, has what direction matrix? What do you notice about those two? They're equal of opposite signs, so what would be the better direction to pick? How about negative 1, 1? Is everybody okay with that? That this here, this, that is the same as minus 1, 1. Is everybody okay? Because I like integers better than that. Well, how did it get that? Well, it has an algorithm that it follows. It doesn't pick smart direction, right? Because we would have an alpha times minus 1, 1, right? We'd have a minus alpha alpha. Well, all right, fine. And so what we found was lambda 1 was equal to 0.92, and x1 was equal to minus 1, 1. And then what's lambda 2? Now here's kind of an interesting thing. It says 1.0000, so it's a little off, but you would just say, I bet it's 1, right? I'll assume it. What do you think x2 is? What do you notice about those two? It looks like if I would take x's second row second and divide it by x's first row second, I'm probably going to get 3. So what is it actually? 1, 3. Right, negative 1 over negative 3, or just simply 1, 3. So that's better. I'm going to call it 1, 3. Is everybody okay with that? All right, well that tells me that A is, I'm just going to write x, because I really don't care, but it's 0.92001 times x inverse. And now we're going to take a little bit of a thought here and say, what does x do to vectors, say vector k? It's going to spit out the next one, k plus 1, the next state vector. Well, that's just simply x times 0.92001 x inverse times a vector k, right? But this guy is in standard coordinates. What's happening? It takes our probability vector, which tells me how many people are living, and switches it into the coordinates of the eigenvectors. But I really don't. But then what does it do to those? It multiplies. What does this do? It multiplies the first coordinate by 0.92, which means where is it going? Smaller. And what does it do to the other one? Stays the same. And then it switches it back. Now, if I do this over and over and over, because this becomes a process, the kth event is the kth power starting off at the 0, right? But that would tell me that this is simply x times, I know how this works, it's 0.92 to the kth power, 0, 0, 1 to the kth power, x inverse times the initial thing in standard coordinates. As k gets larger, what's that? Which means it's going to, what's that? It's 1. So what's happening? What happens here is this guy is switched into coordinates of the eigenspace, but what happens to the first coordinate? It goes to 0. What happens to the second coordinate? It stays. But then what happens? I multiply it by x. But if I have a bunch of numbers times x, what's it going to do? It's x's first times the first, right? The first number here, which would be what? 0. Plus x2 times whatever coordinate this one spits out, which is going to be a number of some sort. So what happens? It goes to a single value. It goes to a vector in the direction of one of the eigenvectors, because all the other coordinates collapse to 0, and he's the one who stays. I just need to figure out the stretching. Where does the stretching come from? Right there. So this Markov process is pretty straightforward to think about if we just simply say that, oh, wait a second, instead of doing all what we used to do, we had to go through it and try to eyeball it, the eigenvalues and eigenvectors are going to help me figure out what's actually happening. And when you have stochastic processes, it allows us that when we see something like this, like that one's going to 0 and this one is simply a 1, we actually have a theorem, which is for a n by n, if the Markov chain converges to a steady state, like this example above did, vector, say x, then what's happened is 1, x is a probability vector, 2, that's because it's part of the system, lambda 1 equals 1 is the guy who determines it, and this is an eigenvalue of A, and x is an eigenvector belonging to lambda 1 equal 1. In other words, that's this guy right here. Because that guy was a 1, what happens is this is a stretching of the eigenvector. So you're in the same direction. That's all that's saying. So that's what's always going to happen on these particular problems. If you have a steady state, that means you had a 1 on your eigenvalues. Everybody else went to 0. This one guy carried off, and so that's the one that forced this stabilization. All right. So that's one thing that we could do with this whole eigenvalue, eigenvector, right? We could imagine these things as bases, and they're just converting coordinates, and this representation of D, works out, and so we can visualize what these things physically do, and so we can talk about transforms and the matrix representation of the transform, and then just let's rather move it to the basis of the eigenvalue vectors, and then ask what the stretchings do. Another example, so another application, oddly enough. Okay, let's do a little bit of, all right, addition is advanced counting, right? 2 plus 2 is actually the ability to count. What we call multiplication is multiple additions. 2 times 3 is 2 plus 2 plus 2, right? We count by 2s 3 times. And so we learned the next step at what's multiple multiplications? What do we call it? Exponentiation, right? Exponents. And so we would sit there and say things like, okay, I know what 2 cubed is. It's 2 times 2 times 2. And then we varied this things to like 2 to the pi, and we would get numbers out, even though it's like, well, wait a second, there's pi numbers of 2s. Yeah, you do a little bit of work, but this idea of an exponential function, right? 2 to the x, and we could visualize it going up like this, right? It's a doubling function. So we've done these sorts of things. So one of the things that we could do is to say, well, wait a second. Exponentiation. If I asked you to find e to the x power, if I said things like, what's 2 cubed? It's 2 times 2 times 2. If I asked you to find 2 to the pi, how would you find it? I mean, what would you literally do if that was a homework in the middle of one, and it was your calculus, and they want to have a number, and you saw that you had to do 2 to the pi? What would you do? You plug it in your calculator, right? You would say, well, what's 2 to the pi power? And so you would have this little calculator button that looks like this, and you'd write 2, and then you'd hit your button, and you would hit pi, and you would hit equals, right? And then it would spit out an answer. My question is, how did it do it? Magic. Well, if you take 451, you actually have to code a program that does it, right? So for Math 451, you're going to have to do it. But what it does is the fact that e to a, where if a is a real number, right, is simply what? It's 1 plus a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed plus 1 over 4 factorial a to the fourth plus ... This is exactly equal if I do how many terms? An infinite. If I stop, it's an approximate, right? But I can always measure how far off I am. But that's this thing right here. Is everybody okay with that? When your calculator does it, it actually does a polynomial. Because all it can do is multiply and add in bit shift. And multiplication is adding. So really just bit shift and add. It's advanced bit shifting and adding. Okay, if you look at that, I have a little idea. What do you think about e to a matrix? It's like, well, that seems, you're telling me, like, what's e, which is the natural number, raised to a matrix power? It's like, well, one of the questions would be, why? Well, but could I just replicate that? Wouldn't it? How about I do this? It's I plus a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed plus ... Can every one of those be done? If a is square, if it's n by n, I, which is n by n, can I add two matrices? Yes. Can I square a matrix? Yes. Can I cube a matrix? Yes. Can I take a scalar and multiply it by a matrix? Yes. Are all of these matrices n by n? Yes. So I should be able to add this entire thing up. In other words, e to a matrix, which would be just, can you add from k equals 0 to infinity of 1 over k factorial a to the kth power, where a to the 0 is considered I? That exists. Can I do it? That's the kind of the question. It's like, well, I can't add an infinite number of times, right? So, I mean, hopefully it would converge, right? If I added more and more and more and more and more, this thing would eventually converge. Is there something going to work on this? And so really, what's the big heart of this problem? The big heart of this problem is a matrix to the kth power. Have we already dealt with a matrix to the kth power? Yes. A matrix to the kth power is easy to do if it is, right? If it's diagonalizable, right? In other words, you know what? If a was equal to x d x inverse, a to the k is equal to x d to the k x inverse. So the heart of this problem is actually d to the k. All right, so that's what I'm going to try. So I'm going to try, what is I plus d plus 1 over 2 factorial d squared plus 1 over 3 factorial d cubed plus dot dot dot. This is actually the sum from k equals 0 to infinity of 1 over k factorial d to the k. But here's the deal. What is d to the k? It's a diagonal matrix. That is lambda 1 to the k, lambda n to the k, 0, 0. What's that times k factorial? That is 1 over k factorial, lambda 1 to the k, 1 over k factorial, lambda 2 to the k, 1 over k factorial, lambda n to the k, got zeros and I got zeros. What am I adding? Matrices. When you add matrices, what are you adding? Their position. So that means this sum actually goes through the matrix. What's the sum of a bunch of zeros? 0. And so that means this is actually equal to the sum from k equals 0 to infinity of 1 over k factorial lambda 1 to the k dot 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 dot. The sum from k equals 0 to infinity of 1 over k factorial lambda n to the k. Those are still zeros. All right, let's go back up to here. Where are we at? There it is. Let's make a dot 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 right here. Dot dot dot. What is that? That's the sum from k equals 0 to infinity of 1 over k factorial a to the k. So if I have something that looks like this, it's actually this if the a is a real number, right? Is that what I got? Those are all lambdas, right? If these are real values, that means what is this? It's e to the lambda 1, e to the lambda n, 0, 0. Oh, wow. E to the d is simply e to the... So e to the d is simply e to the eigenvalues. What? It didn't distribute through. What happened was that all this algebra, it worked out great. It really looks like E just went right into it. Okay. So, but that's only if I have diagonal matrices, right? But A is equal to x d x inverse. Well, e to the a was the sum from k equals 0 to infinity of 1 over k factorial a to the k. But that's equal to the sum from k equals 0 to infinity, 1 over k factorial. What is a to the k? It is x d to the k x inverse. Properties of sums. If you have a k, you stay inside the sum. If you do not have a k, what do you get to do? Take it out. So that tells me that e to the a is simply going to be x times the sum from k equals 0 to infinity of 1 over k factorial d to the k with my x inverse matrix on the other side. And so e to the a is simply x e to the d, x inverse. And so what is e to any matrix? It's the eigenvectors times e to lambda 1 down to e to lambda n, 0, 0, times x inverse. Now we have something we can do. As long as a is diagonalizable, I can take e to that particular matrix power. it'll be a big matrix, right? If I would take this thing, we could still look at this as an actor, right? If I had an object, it would switch it into the coordinates of the eigenvectors, but then I multiply it by this, which means every coordinate is multiplied by this exponential that's associated with it, and then we could switch back into standard coordinates. And so this thing is a stretching still, but it's a stretching exponentially. Well, it's interesting and all that we would have an e to the a power. Why are we wasting our time with this? All right. Everybody remember how we solved that messy looking thing? How did we solve that thing? Anybody remember how we solved that? It's just one section ago. If I gave you this problem and it was a mixture between two tanks, how did you solve this? Anybody have any remembrance? It has solutions. What are the solutions?
Y equals C E lambda.
We'll have all exponential solutions, and the exponential solutions are going to be what? E to the eigenvalue t, right? And then if we have how many eigenvalues, you're going to have that particular many functions, and then we put them together with a linear combination, and we can find the combination based upon the initial values. Was it hard? Everybody somewhat remember trying to stuff all that back together? Everybody try to do the examples of this section? Okay. How did we come up with a solution? What did we do? We guessed and we checked. I have a new operator. You know what? I'm going to guess a new answer. I'm going to guess that the function is going to be e to the t times a. I'm going to guess that that's the answer. It's just going to be e to the t times a. Now that I have such a function, let's check. How do I check? I need to take the derivative with respect to t of e to the t times a. But what is that? That's the derivative with respect to t of I plus ta plus 1 over 2 factorial t squared a squared plus 1 over 3 factorial t cubed a cubed plus dot dot dot, right? Are there any t's in the identity matrix? So if I take the derivative across that thing, what's it going to become? The big zero matrix. So that's gone. All right, so this would be O plus, what's the derivative of that? There's only one t. It's t times this, so what's going to be left over? A plus. What about this? I'm taking the derivative of t. That's a t squared. What happens to that? 2 comes out in front. It would cancel with one of the 2's in the bottom, leaving 1. And so I would have t times a squared plus. That's a t cubed. So what's going to happen? 3 comes out, knocks out one of the 3's. It's going to be 1 over 2 factorial is left. T squared a cubed plus, and this continues on. Everybody okay with that? Now that's not here, right? How many a's are on all of these? 1. If I factor it out, I'm left with I plus ta plus 1 over 2 factorial t squared a squared. That looks awfully familiar. That's ay. So my check was, what is y prime? It's ay. Yay. So that tells me, so y equal to e to the ta is a solution. Not only that, notice y of 0 is simply e to the 0 times a, which would be e to the 0, right? Which would be just simply 1. So if I would let y rather be e to the ta times the initial y0, then not only does y prime still hold, y of 0 will end up being y0. So this is a solution to y prime equals ay, and the initial value y0 equals y0. So this guy is the universal solution. It's the exact specific solution. Let's go back to our mixture problem from 6.2. 6.2 had this tank mixing problem, and it looked like the example in there was A was equal to negative 1/10, 1/40, 1/10, negative 1/10, with initial state of 60 grams of salt and no grams of salt in the two tanks. And I wanted to solve y prime is equal to ay, and y at the initial state was y0. What's the answer? The answer is this. Y is equal to e to the t times negative 1/10, 1/40, 1/10, negative 1/10, all times 60, 0. Done. The problem is entirely solved. No work. Just simply rewrite it down. Now, does it look like what it looked like in the previous one? No. If you wanted to make it look more, if you wanted to make it look a little better, if you wanted to have it say, okay, what do we do? The thing to remember is if you wanted to rewrite it a bit, that e to the ta could be rather written as x, what are the eigenvectors, times a diagonal matrix, which would be e to the t lambda 1 down to e to the t lambda n 0, 0, and then x inverse. And so what you would do is if you wanted to make it look more like make it look exactly like the other one, you would find the eigenvalues, you would find the eigenvectors, you would put the eigenvectors in x, you would put the eigenvectors in x inverse, you would put e to the t lambda 1, e to the t lambda 2, e to the t lambda n, you have these three matrices, and then on the right-hand side is 60, 0. Multiply it all together, you would get exactly the solution from the previous section. So there's nothing to do to solve. So it's a rather useful function because we can solve these with one step. All right, that's it.